Kia ora. Today I'm looking at the 2012 NCEA paper for bonding and energy, and this is question 1a. This question is asking us to draw Lewis structures. Now if you recall, the Lewis structures only use valence electrons. So the first step that I would take in answering this question would be to count up the valence electrons that are available in each of these molecules. So if we start with PCl3, if you look at your periodic table, you can see that phosphorus has 5 valence electrons and chlorine has 7. So it's 7 times 3 plus 5. So we've got 26 valence electrons for phosphorus trichloride. Now, carbon dioxide, CO2, each carbon atom has 4 electrons, 4 valence electrons, and oxygen has 6. So 6 times 2 plus 4. So that's 16 valence electrons. Then we've got H2S, dihydrogen sulfide, and each hydrogen has 1 electron. And sulfur, in the same column as oxygen, has 6 valence electrons. So there we've got 8 valence electrons. Now I'm going to start drawing these diagrams. And as I draw them, I'm going to use single bonds, initially at least, to join up all of the atoms. Now I've put P in the middle here because P is the first atom written in the molecule, and generally, unless it's hydrogen, the first atom that's written is the central atom. Now the other thing we have to remember about Lewis structures is that most of the atoms, apart from hydrogen again, boron and beryllium, these atoms have to follow what's called the octet rule. So they need 8 electrons around them. So just drawn in 3 pairs of non-bonding electrons around that chlorine. And if I count the bond, the electrons in the bond, now remember that is a covalent bond where we're sharing 2 electrons. So we've already used 8 electrons up there. And that chlorine has got an octet. Now if I do the same for the other 2 chlorine atoms, each of them are following the octet rule, and so I've used up 24 electrons. 2 left over. Any leftover electrons generally go on the central atom, and by doing that, that gives phosphorus 8 electrons, 2 electrons in each bond plus the non-bonding pair. So now I've used up my 26 valence electrons, and each of the atoms has got an octet, a filled octet. So that is the correct structure. Now, carbon dioxide, let's have a look here. Put carbon in the middle, join each oxygen on with a single bond. Now we've got 16 valence electrons there, so already I've used 4 of those electrons, leaving me 12. Well, that's handy because that gives me 6 left over. Now if I put those on each oxygen, I've used up all 16 electrons, 8 around each oxygen, and the 2 oxygens have got a filled octet. But there's a problem, because carbon does not have a filled octet. It's only got 4 electrons around it. We want 8. So we go to double bonds. And then we've used up 2, 4, 6, 8 electrons. We've got 8 left over. Each of these atoms needs an octet. So for oxygen, each oxygen to have an octet, it's already got 4 electrons. If we draw in another 4 on each of those, now we've still used 16 electrons, but now all 3 of the atoms have filled their octet. So that's the right structure. That one is not. What about hydrogen sulfide? Now hydrogen can never go in the middle, because it can only form 1 bond, so we're not going to put hydrogen in the middle, we'll put sulfur in the middle. Each of the hydrogens has got 2 electrons now that it's sharing with the sulfur atom, so we've used 2 of our 8 electrons. The other 4, we've used 2 lots of 2, so 4 electrons have been used up in those 2 bonds, and that leaves us with 4 electrons to put on the sulfur atom. Now, hydrogen can only have 2 electrons. It's only got 1 electron shell, and that first electron shell can only hold 2 electrons, so that works for hydrogen. And you could call that the duet rule if you wanted to. And each of the sulfur atoms now has 2, 4, 6, 8 electrons around its central atom. That's a messy looking pair of electrons there. Let's make them all a bit bigger. So we've got an octet in the middle and the hydrogens around the outside, using up the 8 valence electrons. So that structure is also correct.